Okay, the part B to this question involves a rational function. So I'm going to let you read this, but I'll just help you with some of the key parts of this. The main difference with this and part A, between this and this part A solution, is that this is a rational function, and so we have an extra point to consider on the sign diagram of f prime. The sign diagram of f prime will now include the vertical asymptote, where the bottom goes to 0. So I have another point to put on my sign diagram, which means it's going to increase the number of intervals that I test. Okay, everything else stays the same. I'm still classifying the stationary points. I'm still graphing to see what it looks like. Okay, but just keep that in mind. You can read this and then bring me questions to the next class. Okay. Now we're going to have another type of problem here. This is called an optimization problem, and in this type of problem, we're actually we're looking for we're looking at real life applications where we need to find the maximum or minimum points. Okay, and this is where we have a lot of application to real world situations. Okay, so here are the steps to solving these types of problems. Let me just show you what the problem is going to look like here. Okay, we have square corners are cut from a piece of 12 by 12 tin plate, 12 centimeter by 12 centimeter tin plate, which is then bent to form an open dish. Okay, so we have a square like this. We're going to cut the squares out of it, identical squares. What size squares should be removed to maximize the capacity of the dish? Basically, we're going to fold these up and make a box that looks like this. Okay, so to solve these types of problems, since we're looking for a maximum capacity, we're looking for a maximum volume, we're going to have to use a little bit of calculus here. Okay, and the way we're going to do this is kind of the general way to solve these types of problems. We always have to draw the diagram and construct an equation. Okay, building a function. We have to build a function, and this is probably the hardest step. Okay, step 2 is the hardest step because you actually have to create the equation. Okay, and usually the variable that you want maximized or minimized has to be the y value. Okay, that's usually the y value. That is usually the function of the variable that I'm changing. So it has to be a function of some other variable. I have to build a function. Okay, once I find the function, I derive it with respect to the variable that is describing the function, and then it's just one of these problems. Okay, it's just finding the derivative, finding the zeros of the derivative function, and then determining whether it's a maximum or minimum, and that kind of thing. Okay, so let's look at this problem. If I have a square dish or a square plate and I cut it using squares, okay, what size squares, how big should the squares be to maximize the volume of the dish? Okay, so I need to somehow define my variables first. Obviously, the one that I'm interested in is, what variable am I maximizing? Well, it's going to be capacity. So I need to get a volume function. I need to get v as a function of something else. Okay, what am I changing? Well, I'm changing the dimensions of my square, right? So the variable x becomes the independent variable, and the variable v becomes my dependent variable. So I need to build v basically as a function of x. Okay, let me change my pointer here. I basically need to find v as a function of x. Okay, and I need to get something where all of the terms in here have x's in them. Okay, so if this is a 12 by 12 tin plate square originally, Well, if I make this x and this x, since they're squares, okay, then this becomes 12 minus 2x, because I have two squares on either side. So I have 12 minus 2x, and this is also 12 minus 2x, right? So this is 12 minus 2x, this is 12 minus 2x, and this length is x. So when I fold it, I'm going to get a box that looks like this. Okay, so now I've created a function. I can find the volume of this box just by changing the size of the square that I'm cutting out. Okay, and now the question is, well, what's the biggest volume? Okay, so I need to find the maximum volume for all possible x's. Okay, so the important thing about these types of functions is usually they're real-life problems, so there's a restriction on the domain. Like usually it's impossible to have a negative length or some length bigger than a certain number. And in this case, x has to be bigger than 0, and x has to be less than 6. How did I come up with 6? Well, this is 12, right? This distance is 12. So if I made x up to 6, well, once I go past 6, I would be cutting into this. I'd be cutting into this where this guy should be cutting, so I would have no box left. So 6 is the biggest possible square that I can make, or really close to 6, and 0 is the smallest square that I can make. Okay. Volume or capacity of a rectangular prism is length times width times depth. Okay, or length times width times height is what I would prefer, but this is fine. So we have 12 minus 2x times 12 minus 2x times x. So now I have a function of x, which is my volume. My volume is described in terms of x. So once I have v, which is this function here, then I take the derivative of that with respect to x. Okay, if I find v prime, I end up with this function, and then now it's the same thing as what I did in the previous example. I am going to take this, find the zeros, find the stationary points basically, and determine if any of those stationary points are maximum or minimum values. So if I factor out a 12 from each term, I get 12x squared times the quantity x squared minus 8x plus 12. This factors into x minus 2 and x minus 6. And so I have 2 points that I'm interested in. I have two zeros, right? A 0 at x equals 2 and at x equals 6. But really, 6 is at the end point of my domain, so I don't need to check anything past 6. And I don't need to check anything lower than 0. So I'm going to put in a number between 0 and 2 into here. If I put 1, this is negative, and this is negative, and this is positive. So it's positive times negative, that's positive. So this whole thing is positive here. If I put in a number between 2 and 6, let's put 3. If I put 3, this is positive, and this is negative, right? 3 minus 6 is minus 3, so that's negative. So it'd be a negative total. So v prime is negative here, v prime is positive here, which means it's increasing. V is increasing. Remember, this is for v. Okay, this is v, not v of x, v prime. That's v. So v is increasing and decreasing. So it's a maximum at x equals 2. All right. This is how useful derivatives can be in real life context. So the biggest volume would be formed by a square of 2 by 2 centimeters being cut out from this tin plate. All right, so that's it for this section. Please look at the examples carefully, and if you have any questions, let me know. All right, thanks.